Welcome back. The objectives of this video are to apply some real-world examples to exponential models. And at the end of the video, we'll even write a model given a real-world scenario. We'll write an exponential model. So let's take a look at example 1 here. Surfside High School was built in 2007 and has a growth rate of 1.8% each year. The initial student population, A sub 0, is 1,483 students that year, so in 2007. So 2007 is going to represent year 0, and the rate R is written at a decimal. They're asking us to write an exponential model, A sub t, given A sub 0 equals 1 plus R to the t to represent this scenario. So our variable is t. A sub 0, well, that's going to be the 1483. They gave that to us already. So A sub t equals A sub 0, 1483. We got that right out of the word problem. Times 1 plus R to the t. Well, we have a growth rate, R, of 1.8%, or 0.018. But plus 1. So 1 plus 0.018, kind of like the sales tax example. So we've got 1.018 as our R now, all raised to the t. We've taken care of problem A. On B, it says use your model to find the expected student population in 2024. Well, remember that 2007 is year 0, 2008 would be year 1, so a little subtraction, 2024 minus 2007, and we get 17 years. So A sub 17 equals 1483 times 1.018, all raised to the 17th power. Now this I'm going to have to put in my calculator, so I will go ahead and do that and get our final answer. So I got my calculator out. I've got 1,483 times 1.018, all raised to the 17th power. And it gives me 2,008 students would expect to be enrolled in 2024. So the 2,008 students is our expected student population. In the next sample, we're going to use doubling time. So our formula here, P of t, so t is our variable time. P sub 0 would be our original or initial size, or our size at time 0. We're doubling, so our ratio R is going to be 2, and all raised to the t over k, where t is some time and the doubling time is k. So doubling time is k. So the amount of time it takes to double, and make sure your k and t are in the same units of time. So example 2 says a certain fish species was introduced into a tidal basin 10 months ago. So the 10 months is going to be the amount of time. So we see here that t is equal to 10. The current fish population is estimated to be 220. That is our output. This is a y value, our current fish population. So that's our P of t is equal to 220. It's not our original amount, but it's our current amount. We want to find the initial size. So our doubling time is 5, so k is 5, and we need to find P sub 0 is our unknown. So putting everything into our function, we have our 220 equals our output, P sub 0 is our unknown, we are doubling, and our t over k is 10 over 5. So 220 equals P sub 0 times 2 squared, which is 4. We divide both sides by 4, and we get 55 equals P sub 0. So we can estimate the initial population of fish was 55 fish. Estimate the population of fish 1 year after they are introduced in the tidal basin. Well, everything here is in months, so 1 year we're going to convert that to 12 months. So now we want an estimate after 12 months. So our P of 12 will equal our initial estimate of 55, the doubling of 2, T is 12 over 5. I'm going to put that in my calculator, 55 times 2 to the 12 fifths, and I get 290.292 fish, or 290 fish after 12 months. In example 3, so suppose the half-life of a certain radioactive substance is 40 days. So now our since its half-life will be 1/2 of a certain radioactive substance is 40 days. That 40 days is our K. And there are 8 grams present initially. So P sub 0 is 8. So we've got, in this case, I guess it's A sub 0 is 8. Our K is 40 days. Find the time when there will be 1 gram of substance remaining. So that will be our A sub T equals 1. We want our output to be 1. And we want to find the time, so T must be our unknown. Putting everything into our function, we get A sub T equals 8 times 1/2 T over 40. Well, A sub T is 1. Our Y is equal to 1. We want to find out when it's equal to 1. So what we're going to do here, since we don't have the algebra skills yet to solve for T and the exponent, we're going to go to our graphing calculator and graph this. And we're going to graph 2 equations. We're going to graph 8 times 1/2 T over 40, and we're also going to graph Y equals 1. And then we'll find the intersection using the calculator. So use the calculator to find the intersection of Y equals 1 and Y equals 8 times 1/2 raised to the T over 40. So I've taken the liberty to put the 8 times 1/2 raised to the x over 40, and notice how my liberal use of parentheses here to make sure I have my order of operations correct. That is one of my equations, and the other equation is Y equals 1. And I want to graph these guys simultaneously. Now, we do have to consider our window here, so if we go back to our data, if our doubling or our half-life is 40 days, don't we know that to go from 8 to 4 is going to take 40 days? And then to go from 4 to 2 is going to take another 40 days. So add another 40. And to go from 2 to 1.5 is going to take another 40 days. So I found the answer arithmetically by using the half-life. That was a pretty easy example. But as we keep going, it's going to take 40 days, 40 days, 40 days. So I just found the answer is 120 days. But let me show you how to do this with your calculator. So with our calculator, let's go ahead and set up our window. we just saw that our x's are going to be out to like at least 120 days. So I did my x's from -5 to 160. I counted by tens. And my y's, my amounts, will never be less than 0, but I'll do -2. And I did a y max of 10, so I could just see that. And then I get this nice graph of our exponential decay function in blue, our y equals 1 in red, and then I just want to find the intersection, so I go to second, calc, find the intersection 5, select the blue curve, select the red curve, make a guess, and answer, and sure enough we get x equals 120. So then finally I can say it'll take 120 days to decay to 1 gram, but there you can see another way we can do the intersection on our calculator to find our answer. And here in example 4, we have a graph shown at right with a couple of points, -5, 12, and 6, 1/2 labeled. And we want to write an exponential model for the graph. So we're going to use our model y equals a times b raised to the x. So in order to find our model, we actually need a and b. So we need an a, we need a, and we need b. The good news is we have 2 x's and 2 y's. So we're going to set up a system of equations in 2 variables using our x's and y's. So we know that when y is 12 equals a times b to the -5. So I'm using the first ordered pair, -5, 12, and I'm putting it into the function. Well, that's also 12 equals a over b to the 5th, or multiplying both sides by b to the 5th, now I know 12 times b to the 5th is equal to a. Using my other ordered pair of 6, 1/2, I do the same thing. 6 equals a times b to the x, a times b to the 6th, and that's not 6, that's 1/2 there because that's my y value. So I have 1/2 equals a times b to the 6th. Well, if I know a is 12 times b to the 5th, I can then say 1/2 using the substitution method. I'm going to put this a value into the other equation. So I get 1/2 equals 12b to the 5th a times b to the 6th. So 1/2 equals 12 times b to the 11th. Now I can solve for b. So if I divide both sides by 12, I get 1 over 24 equals b to the 11th. I take the 11th root of both sides to solve for b, and I get b is the 11th root of 1 over 24. So b is equal to approximately 0.749. I had to use my calculator to get that, but that's what b is. So now I know what b exactly is, and let's take a look and see where we're at here. So just to our left here, if we see that a is 12 times b to the 5th and b is 0.749, then we know that a is equal to, by doing substitution, right, I can just take this b and I'm plugging it in right there. So a is equal to 12 times 0.749 to the 5th. So then I know a is approximately equal to 2.8287. I did that by just putting that in my calculator. A is 12 times 0.749 to the fifth. A is 2.8287. So now I know what both A and B are. A is 2.8287. B is 0.749. Now I can have a function. My function is y equals 2.8287 times 0.749 raised to the x, or question B then says, what's the y-intercept? So for the y-intercept, we set x equal to 0. So y equals 2.8287 times 0.749, all raised to the 0. So all this drops to 1. So when x is 0, y is 2.8287. So it's the ordered pair 0, 2.8287. And that is that point. Oops, I missed. That is that point right on our graph. 0, 2.8287. And there you go. You have now written a mathematical model for an exponential decay function, and you'll get some more practice with that when I see you in class.